Hey, welcome back. We got some really cool stuff today with similarity, so let's get started. Before we talk about similarity, let's talk about something we already know, which is congruency. And the postulates for congruency are very similar to what we're going to be doing with similarity, just one minor difference. So with congruency, the symbol is broken down into two parts. We have the tilde, which tells us it has the same shape, which comes from the same angle. So in this case here, we have parallel lines, so the alternate interior angles are congruent, and these alternate interior angles here are going to be congruent as well. Now that we know that the alternate interior angles are congruent, we know two of the angles are the same, so the vertical angles in the middle also have to be congruent, or we could do that from the third angles theorem as well. So these two triangles have the same angles, which tells us that they're actually going to be similar to each other, but not necessarily congruent. The only way that we would be able to prove congruency is if we had a side length. Remember, it's not enough to have just the angles. That actually proves similarity, but not congruency. So if this blue line was bisected or cut in half by the other line, then that would mean that we could prove that triangles are congruent by angle, angle, side, like we did when we talked about this last. So let's see what happens when they don't have to be congruent, because it's much more interesting when this is allowed to move. The angles are still the same, and these triangles are still similar. They have the same angles, right, with the alternate interior angles and vertical angles being the same, but they no longer have the same size or the same length of the sides. So let's get rid of that condition and see what happens now. So let me take this, and if you notice, I've actually measured out the lengths here. We have 8, and this length here is 6. So we're going to see what happens. So this top length here is 2, and the bottom length here, if that's 2 out of 8, the rest is going to be 6, right? So this is going to be 2 out of 8, and this part here is going to be 6. So we have a length of 2 and a length of 6. And then what's going to happen to the other part? So the blue part is going to be, I believe, 1 and let me see, actually. So it's going to be 4 and a half and then 1 and a half. Yeah, so we could basically set up a proportion. I believe if I do this right. So we have 1 and a half and 4 and a half. Yes, exactly right. All right, so we can set up a proportion, and we see that 2 goes to 6 just as 1 and a half goes to 4 and a half. So that's us setting up our proportion. Let me get rid of that. I wasn't supposed to have that there. Okay, so 2 goes to 6 just as 1 and a half goes to 4 and a half. So what's going to happen is that this the blue line is going to cut the other line proportionally, and in fact all of the sides are going to be proportional. I just didn't show the other line in this case. So if I cross multiply in this proportion, I have 2 times 4 and a half is equal to 6 times 1 and a half, which is going to be 9 is equal to 9. So sure enough, these two sides, they cut each other proportionally, which is interesting. They don't bisect each other, but they cut each other proportionally, which is fascinating. Now this is not only true if I go to 2, I can do the same thing. Let me reset this real quick. So if I go to 3 here, so I have side lengths of 3, and the other one's going to be 5. So this is 5 and this one's 3. And then the other lengths I have here, if I measure them out, the blue line is going to be, looks like 3.75 and then 2 1/4. So let's see if I did that. Yeah, 2 1/4 and 3.75. So if I set up this proportion again, 3 goes to 5 just as 2.25 goes to 3.75. And when I cross multiply these, I'll get the exact same thing of 11.25 is equal to 11.25, which is fascinating, absolutely fascinating. So both of these, regardless of how we do it when I cross multiply, I'm going to get that these are going to be congruent. They're proportional. So in this case, they are these two triangles are going to be similar to each other by angle, angle. We also could show that if we have two triangles that or figures that are similar by angle, angle, if it's triangles in this case, then that means all the sides must be proportional. And we could measure the lengths of their hypotenuses as well if we wanted to, and they would have the exact same proportion, which is absolutely fascinating. So not only can you see as these grow and one of the other one shrinks, it's kind of a trade-off between the two. Isn't that just so aesthetically pleasing? But we can actually measure them out at any given time, and we'll see that they'll actually be proportional. I just gave you 2 examples of when they were, which is really, really, really cool. So that's what we're getting into with similarity. They have the same shape from the angles, but not necessarily the same length of the sides. The sides are going to be proportional. So in order for it to be similar, all of the corresponding angles must be congruent, and the corresponding sides must be proportional, meaning they have the same scale factor, whatever that scale factor is. So are these two figures going to be similar? Well, if we look at this one, we need to first find out what sides are corresponding. Well, the smallest side over here, 4, is going to have to correspond with the smallest side over here. So if we blow it up, the small side is still going to be the small side. It's just going to be bigger, right? So that means that 4 is going to correspond with the 6. Then the next smallest side, 6, we like to go in order from smallest to greatest. Just you can actually set this up many ways, but it's easier if we just do it the same way over and over again, just getting the pattern of it. So the next small side is 6, and that's going to go with the next small side of 9. So 6 corresponds with 9. Then 8 goes with the 12, and then the longest side of 10 is going to have to go with the longest side of 15. So we just set up an extended proportion to check to make sure that all the sides are indeed proportional. Now if we look here, it looks like they said all 4 angles are the same as all 4 of these angles. So we do know that the angles are congruent, but when we're proving similarity with figures, at least bigger than with more sides than a triangle, it's not enough just to know the angles. We have to know that all the sides are growing at the same proportion or the same rate as well. That's because a square and a rectangle both have the same angles, but not necessarily are they proportional, because obviously a rectangle is allowed to be stretched out longer than a square, which has all the sides are the same. Okay, so what we're going to do is cross multiply to check this. So we're going to say or another way, actually, so 4 times 9 is equal to 6 times 6. That's true, yeah. 36 is equal to 36. Here we would have 72 is equal to 72, and then 120 is equal to 120. So we can cross multiply all those and check, and indeed they are proportional. Another thing you might notice is you can actually reduce all these fractions to the exact same thing. So that one's 2/3, this one is 2/3 as well, this one is also 2/3, and the last one is 2/3 as well. So if we can reduce them all to the same fraction, then surely they have to have the same ratio and the same scale factor, and that is their ratio, by the way, 2/3, and the scale factor would just be the reciprocal of that, which is 3/2, by the way. All right, so finding the scale factor, we want to do the image divided by the preimage. So we started out at 4. We usually go left to right. So we're going to do the image of 6 divided by 4. So 6 divided by 4, which is basically 1.5 if you put it in the calculator. So our scale factor is 1.5. So everything gets multiplied by 1.5. So the longest side of 10 becomes the longest side of 15. So if you notice, this whole image is actually rotated, which makes it kind of tricky to match up the corresponding parts, because 8 doesn't go with the 15. The biggest side of 10 goes with the longest side of 15. So that's why I always go from the smallest to greatest. It'll help you out with that. Now the ratio going from left to right is going to be 4 to 6. That would be the unreduced ratio. Then we can reduce that, take a 2 out, which would be 2 to 3. All right, so are these two similar? So two things we have to check for similarity again. Are the corresponding angles congruent? Now both of these are rectangles, they got the same angles, so that part's good. Now with the triangle, that would be enough information, but when we have polygons with more sides than just 3, more than a triangle, then we have to actually check the side to make sure they're proportional as well. So my smallest side of 4 is going to go with my smallest side of 5, and there's 2 4s and 2 5s, so yeah, that's not that big of a deal. And then the longest side of 10 goes with the longest side of 12. So set it up, 4 goes to 5, just as 10 goes to 12. Now, you can obviously see those are going to be the same. 20 is equal to 20, 120 is equal to 120. So what we really want to see is if we cross multiply here, are they equal to each other? So 4 times 12 is going to be 48, and then 5 times 10 is going to be 50. Now 48 is really close to 50, but it's not exactly equal. So these two are going to have different proportions. Another thing we can do is reduce this fraction here, which is going to be 5 out of 6, and 5, 6, and 4/5 are two different fractions, so that is not going to work either. So are they similar? No. So they are both rectangles, they have the same angles, but they're growing at different rates, kind of like me. So when I was young, I would grow vertically, and now I only grow horizontally, you know, as I am making fun of myself. But anyway, so we want to make sure that we're growing, if we do have a scale factor, that the height is growing at the same rate as the width, essentially, so that it has to grow all at the same rate by the same scale factor. All right, what about these two triangles? Now, they're telling us that they're similar to each other, and we now want to set proportions to solve for x and y. So the side lengths that they give us that are corresponding is 6 and 36. So I can set my proportion. I know 6 goes to 36, just as what goes to what. Now, there's two ways we can do this. We can set up proportions, or we can do scale factor. Now, the easiest way, actually, believe is just to do scale factors. So especially when it's this obvious, right? If we're going from 6 to 36, what are we multiplying by? Well, we multiply by 6, right? We can find that scale factor by doing the image over the pre-image, which is 36 over 6, which is just 6, right? So same thing, you can find the ratio. We can do it while we're here. So 6 goes to 36. That's the unreduced ratio. We reduce that, and so 1 to 6, which if you notice is just very similar to scale factor. It's just written as a ratio, and this one's written as a fraction. All right, so if I know I'm multiplying by 6, if this triangle is 6 times as big, that's the rate that the bottom is growing at, then what are the rates that the other two sides are growing at as well? Well, if it's similar, they're going to grow by 6 as well, times 6. So 4 times 6 is going to make this one, what, 24? Yeah, and then 5 times 6 is going to make this one 30. And that's actually true. So the other way you could do it is setting up a proportion. So 6 goes to 36 just as, I think we'll do 4 goes to, we called it x before because we didn't know what it was. We can set up another portion. We can go 6 goes to 36 just as 5 goes to y before we knew what that one was. And then we can actually cross multiply or reduce first. So remember, that's 1 out of 6, and this is also 1 out of 6. So now I'm going to cross multiply. So 1 times x, which is just 1x, is equal to 4 times 6, which is 24. And then 1 times y is equal to 5 times 6, which is 30. So yeah, we got it right. Kind of cool. All right, so are these triangles similar? So we want to try or check the similarity with side, side, side. So with the triangle, we can actually, if we know all 3 sides, we can check to see if they're proportional, and that would mean their angles would have to be congruent. The corresponding angles would be congruent. So on this one, notice we need to look at the corresponding parts. So DF and AC, so the blue part and the blue part are corresponding. DE and AB, the red part and red part, and the green part goes with the green part. Okay, so setting up an extended proportion, we have 14 goes to 2, just as 21 goes to 3, just as 28 goes to 4. And notice I'm setting these up from least to greatest, that way you can also check. All right, so we can actually reduce these fractions if we want, or we can go ahead and cross multiply. But if I do reduce all these fractions, they're all going to go to 7 over 1, right? So that's 7 over 1. This is also 7, and this is also 7. So we have 7 is equal to 7, which is equal to 7. So this is true. They're all growing at the same rate. And by the way, that rate or that scale factor is just times 7, right? So 2 times 7 is 14. 3 times 7 is 21. 4 times 7 is 28. So you could even check it with the scale factor. It's pretty obvious. So what is our scale factor? Well, image divided by pre-image, 14 over 2 is going to be 7, sure enough. And the ratio 2 to 14 is unreduced, but reduced would be a ratio of 1 to 7. So pretty cool. All right, write an extended proportion that relates, well, actually, let me go back here. There are 3 different ways to prove similarity with triangles. That's what we're going to talk about tomorrow. We have side, 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 angle, side, and angle, angle. So angle, angle is pretty simple, but side, 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 angle, side, we have to check to make sure those sides that we're given are going to be proportional, meaning we have to set up proportions for them. So really easy stuff we're going to be doing today and tomorrow. I hope you guys enjoy it. All right, so number 1, write the extended proportion that relates the corresponding sides for the similar polygons. So they give us a similarity statement, just like a congruency statement, but it's a similarity statement this time. And remember, it tells us all the corresponding parts. And we know all those corresponding angles must be congruent, and the corresponding sides must be proportional by the same scale factor, the same proportion. So let's write an extended proportion for this. So the first 2 AB goes to the first 2 WX, just as the first 2 BC goes to the middle 2, XY. And then the last 2, CD, is going to go to the last 2, YZ, and then the first and last AD goes to the first and last WZ. So that's how we could set up our extended proportion. We went left to right, left to right, left to right, left to right. Same thing going here, and then top to bottom, top to bottom, top to bottom. All right, so kind of cool and aesthetically pleasing with the rainbow there. On number 4, we want to check to see if the 2 images are, or the 2 figures are similar. So we have to check 2 things. We have to check to see if all the corresponding angles are congruent and if all the sides are going to be proportional. On this one, on number 4, it looks like we have a rectangle with 4 right angles, but the other one only has 2 right angles. So they don't have the same angles, and so they cannot be similar. So they ask if they're similar, we're going to say no, because the corresponding angles are not congruent. So corresponding angles not congruent. Number 5, So are they similar? Well, if we're looking at the angles, so far the angles look like they're the same. We have two right angles and two right angles. We don't know the other two angles, but we'll check the sides instead. So we need to now check to see if the sides are proportional, because remember, two rectangles have the same angles, but a rectangle and the square are not necessarily similar because the rectangles can grow at different rates. Okay. So are the sides proportional? Good question. So by setting up the proportion, I'm going to start with the smallest one. So I'm going to do 2.5. And then the next smallest is 3, and then 6, and then 6.4. Okay, so I went smallest to largest on this side. I'm going to do the same thing, smallest to largest on the other side. So 2.5, 3. Oh, look, those didn't change at all. So this one didn't grow vertically, but it did increase horizontally, kind of like myself at this point in my life. My metabolism slowing down. And then these two are actually growing horizontally. So if this one can't work, right? Because the only way that they would be similar is if, as long as it's not growing vertically, it can't grow horizontally either. So they would actually have to be congruent to each other, but it's not. So if we cross multiply in the middle here, we get 3 times 9, and then which is 27, and then 3 times 6, which is going to be 18. And that's not going to work because 27 is not equal to 18. So I forgot to do the not equal to part. So clearly, these two are not going to be similar because their corresponding sides are not proportional. So no, because the sides are not proportional. We can just say it that way. On number 7, we have two triangles here. They give us all the sides. So we can check the sides to see if they're proportional by side, side, side. And then the angles, looks like they both have one right angle. They don't give us all the angles, so we can't prove it by angle, angle, but we can prove it by side, side, side. Or in fact, because they do have the same angle, we could do side, angle, side, side, angle, side. We don't even need to check the hypotenuse. So let's set up our proportion here. We have the smallest side of 3, and the next smallest of 4, and then the longest of 5, and then over here the smallest of 8, and then the next smallest of 12, and then the longest of 15. All right, so we're going to cross multiply to check. So 3 times 12 is 36, and then 8 times 4 is going to be 32, I believe. Yeah, so 32 is not equal to 36. So they are not going to be proportional. And in fact, those are the only ones we have to check because the 3 and the 4 and the 8 and the 12, the two smallest ones, they have the congruent angle in between them. So we would actually be proving similarity by side, angle, side similarity. So they are not similar by side, angle, side, which is kind of cool. So are these two going to be similar? We're going to say no, because the sides are not proportional. Number 9. On this one we have, it looks like the angle's 49, 49, but this one's 88 and that one's 43. Okay, so only one of the angles are the same. But if we look at the missing angles, if we add those together and subtract from 180, we get 43, which is the same as that one. And if we look at the missing angle over here, it's 88. So they actually, in fact, do have the same angles. So technically that would be enough information to prove similarity with angle-angle similarity postulate because it is a triangle. But let's go ahead and check the sides while we're at it today. So setting up an extended proportion, small side of 4, then 6, then 8. Smallest side 6, 9, 12. So 6, 9, and 12. This one's actually pretty obvious because we can reduce these fractions, right? That's going to be 2/3. That one's clearly 2/3 as well. Divided by 4, that's also 2/3. So clearly they're all going to be exactly the same. And we could, if we wanted to, we could cross multiply them and we would get that they're all the same thing, right? So 36 is equal to 36, 72 is equal to 72, but after I reduce, we get 6 is equal to 6 on all of them. All right, so are they similar? Yes, because two things, their angles are congruent and their sides are proportional. So angles are congruent and sides are proportional. So on number 10, we have a model of the building with given dimensions 4, 9, and 12. And then we have the actual building here. And they tell us that the scale from the model is 1 inch is 15 feet in real life. Then if the model has a width of 9 inches, then what would the width be in real life? So there's two ways we could do this. You have your scale, so you could set up a proportion. So 1 goes to 15, just as 9 goes to what? And then cross multiply. That's totally fine. But this one's actually way easier if we just find a scale factor. So if I'm going from 1 to 15, what am I multiplying by? So image divided by pre-image, 15 divided by 1 is 15. So our scale factor is times 15. So what's 9 times 15? Well, that's going to be 135 feet. Okay, so then if we have a height of 4 inches, again, same scale factor times 15. That's going to be 4 times 15 is 60 feet. And then 12 feet times 15 is going to be, I believe, 180 feet. So real simple. Once you have your scale factor, you pretty much got it. Now the last two, they tell us the actual is 90 or 48, and we want to work backwards and find out how many inches tall the model would be. So it's like if we're making a model of an actual building instead of making a building from a model, just working backwards. Well, if now our image is going to be the 1 inch, and then the 15 feet was our pre-image, so we're just flipping the fraction, right? So if we multiply it by 15 going down, then going backwards, we're just going to divide by 15. So if the actual is 90 feet, we just do 90 divided by 15, which is going to be 6 inches. So this would be 6 inches. You could set up proportions to solve these, but scale factor is easier. And then if the height is 48 in real life, we divide it by 15, and that will give us 3.2 inches. Number 12, determine whether each statement is always, sometimes, or never true. So two squares are similar. So if we have two squares, they have to have the same angles, right, because they're rectangles. And then are their sides always going to be proportional? Well, if their sides are always congruent, then, you know, to themselves on each one, then yeah, they'll always be similar to each other, because whatever the growth from one side to the next one, they're all going to have that exact same growth. So all squares are similar to each other, and some of them are congruent if they have the same sides as well. So that one would be always true. Two congruent triangles are similar. So if two triangles are congruent, which means if they're congruent, yes, they have to be similar. It's a part of the symbol. So it's kind of silly, but yes, that is always true. The reason for that is if they're congruent, they have the same sides and the same angles. All the corresponding parts are congruent. And so they just have a scale factor of 1, or a ratio to 1 to 1. But yeah, sure, congruency is a special case of similarity. So that's always true. Number 17, this is such a cool problem. You want to enlarge a 3x5 photo. Back when we used to print off photos, and before they were just on your phone. This is a real question. The paper you're going to print on is 8.5 by 11, which is like your homework assignment, that standard sheet of paper. So what's the largest that we can make the photo? Well, first thing I kind of want to know is which one's going to run out first. Am I going to run out of my width or the height here? So if I double this 3 and 5, that would become 6 and 10. And it looks like the 10 is going to go to 11 first. So that's the part that's going to run out. This 10 is going to run out first. So I'm going to, whenever I enlarge this photo, the 5 is going to go to 11 before the 3 can get to the 8.5. So I'm going to do 5 goes to 11, just as 3 goes to something. Now I know this one's going to be short. It's not going to make it all the way. In fact, if I wanted to show you where it's going to go, because this is actually the scale, it's going to go right there, which is kind of cool. I mean, if this reminds you of like 1-point perspective and all the blowing up of puppies that we did, it should, because this is our origin here, and it's just increasing by that. So the question is, where are we going to be at over here? In fact, I'm actually going to draw that line going across here. So that's how large we're going to get it. Then the next question we're going to have is going to be how much area is wasted. So the wasted area, let me do it in purple, is going to be this area right here. So what is the area of that wasted part? All right, so first let's figure out what this dimension is here. So we said 5 goes to 11, just as 3 goes to, we'll call it x in this case. So we cross multiply 33 divided by 5, which is going to give us 6.6. So the next question, so this would go up to 6.6 instead of the full 8.5. What's the area of the paper that's unused? So the area of the entire piece of paper is 11 times 8.5, which is going to be a decimal there, of 93.5. The area of the photo that we did use was 11 times 6.5, or 6.6, which would be 66. So then the question is, what area is unused, the purple part? We subtract these two, right? So 93.5 minus 66 is going to give us a difference of 27.5 inches. What a fascinating question. Where will we ever use this in real life? Well, unfortunately, you'll find out on the next question about, you know, anyway, there's a meme I should have showed you, but I didn't. So, all right, in the next diagram, we have our similarity statement. Now, the similarity statements are really important because if we look over here, they all look the same. I mean, these two sides are really close to each other. Which angle goes with which one? Is it rotated, flipped? We have no idea. So follow the similarity statement. Just like on that test when I tricked you guys on the first 3 problems, don't be fooled. So let's find the unreduced ratio from PRQ. So PRQ, that's one on the left to the one on the right. Well, I think 20 goes to 24, but let's be careful. And I have the only side I have over here is DF. So DF is the first and the last. So that's going to go with the PQ, which is here. Okay, first and last. So yes, 20 is going to go with 24. So that's our unreduced ratio. Reduce it, we can take out a 4, I believe, which is going to go with 5 to 6. Yep. And then what's the scale factor? Well, that's going to be 6 divided by 5, which is the same thing as 1.25. So you can take 24 divided by 20. That'll give you the same thing as well. So find the measurement of angle R. Well, R, middle one, corresponds with E, the middle one as well. So R has to be the same as E, which is 35 degrees. Okay, cool. No big deal. Find angle P. Well, P is the first one, corresponds with D. Ooh, I don't know D. Oh, but I can find P because I have two angles of a triangle. So add these together, find a supplement, just like we did on the last one. It's 56. Okay, then D, which is going to be corresponding with P, has to be 56 as well. Okay, no big deal. All right, last ones. Finish setting up a proportion to solve for DE, then cross multiply to find the length of DE. So on this one, we know that 20 goes to 24, just as DE, so DE was the first two, goes with PR. So 20 goes to 24, just as what goes to DE? Just as PR, which is 40. Okay, just as 40 goes to DE. Okay, then you can cross multiply, just multiply 20. Ooh, before you do that, remember we could actually reduce this. What was that? That was 5/6, right? And then you could actually reduce this one, which is going to be 8 and 4. No, sorry, 8 and 1. My bad. All right, so DE is actually going to be 48 because it's 6 times 8 is 1 times DE. So DE is equal to 48. How cool. Love it. All right, next one we know 20 goes to 24 just as what goes to EF. Well, EF is the last two, so that's the first two, or last two here, it's RQ, which is 36. Okay, cool. So this one is going to be 36, and then we can do some reducing again. This is going to be 5 and 6, but 5 is not a common factor with that, so I'm just going to have to cross multiply. Or you know what? You can cross multiply. All right, so cross multiply those and you get the length of the last one, which should be on the answer bank as well. If you have any questions, let me know. I'll see you guys later.